the choice of numbers is by no means random. Because like nobody's picking the square root of pi, you know, comma e normalized. Yeah. I'll begin with a word of prayer. Yeah. Oh yeah, I'll top hat. Dear Heavenly Father, we thank you again for this day. Just ask that you just guide our steps today and help us to understand more about the gradient as a vector field, Lord. In your name I pray, Lord Jesus. Amen. Top hat, you say. That's a good point. I should top hat. I should have topped hat like 5 minutes ago. I do have a brand new, a fresh roster to start working on, so there's that. But I know top hat's very insecure, and if I don't use it, it'll feel, you know, like I've left it for someone else. Although I have. I have. It's true. My infidelity to top hat is well documented. Let's see here. 0802. Why do it once when you can do it twice? Sorry if you missed it. Don't worry, there's another chance. Oh, ooh, look, this one. This is a better one. Right? Come on, I mean, that. What do you think? Anybody want to guess the next one?
1362.
We have a 1, 2, 3, 4. If that.
63.
40. All right, anybody who's right, 20 bonus points.
Hey.
Let's see here. See right here.
1362. 4562.
Oh, so sorry.
No.
Let that be a lesson to you. Don't gamble. All right.
It was right there.
All right. So, silly nonsense aside, let us go on here. And I should hand out the, you know, what's that thing called? The roster, the actual attendance. All right. Get my markers out here. So we've talked about the directional derivative in terms of quantifying the rate of change of a function at a given point in various directions, right? But there is more. We should also think about, lest I forget, in problem 33, the first 2 sentences are nonsense. So like just, you can start reading at let f of xy equals sine of x squared plus y squared over x squared plus y squared. Like the first sentence is, find the domain of f and determine where f is continuous. This no longer makes sense as we've crossed out the first formula. So it's irrelevant because the domain is given to you to be the whole plane. So like the next sentence clarifies that f of x is defined for everything in the plane. And the problem of this problem is just to figure out what a needs to be to make it everywhere continuous. All right. And for the most part, you just need to figure out what's the limit at 0 there and make it match the value of the function. Can you add a date for me? Where are we on the 9th? All right. So let's talk about the gradient vector field. And what's it do? What's its meaning? How can we visualize it? But before I do that, I really just need to take a step back and remind you guys that in R2, right? If we have f of x comma y, I usually use a big F here. Big F of x comma y equals to, you know, say 0. But you could put a constant here, right? You could put 0 here. You could put a constant. Let me put a constant. I'll say c. This defines is a what? It's a level curve. All right. Whereas if we're in 3 dimensions, if we have f of x, y, z equals to a constant, this is what's known as a level surface. All right. Let me just start with a couple really simple examples. So example 1, if we had f of x comma y equals to x squared plus y squared, right, equals to, let my constant be r squared because, well, and then you know what it is, right? What is that?
Circle.
That's a circle, right? Or it's the origin. right? It's a circle, or it's just the origin if r equal to 0. And what's the gradient to this? What's nabla f? Well, it's 2x, 2y, right? That's the gradient. Hey, we can picture this, can't we? So in other words, the gradient is basically twice the, vector out from the origin. It's just 2xy. So if I use my usual notation of like r for x comma y, like that, then, well, we can draw some some level surfaces, yeah? They are, surfaces, listen to me. We can draw some level curves, right? They're just like that, right? Just a family of concentric circles centered at the origin. That's what the level curves are for this function. So this is the neat thing about the level curve formalism is if you give me a level function, I don't just get one curve, I get a whole family of curves that are related in some sort of nicely regular way, right? Not an accident that any point in the plane is on one circle and just one circle, right? These circles, you could say, they're said to foliate the plane. Like, every point on the plane is on a unique circle. If we're talking about circle centered at the origin, of course, if you're not insisting that your circle be centered at the origin, well, there's infinitely many circles that go through a given point, right? But if we're insisting that the circles be centered at the origin, every point's on a unique circle. If we include, the origin itself as a degenerate case, right? Now, if I visualize the gradient vector field, what's it look like? Well, it looks something like this. You see, it points in the direction of r hat, right, which is just radially outward. And we should picture it. The way to picture the gradient vector field is if it's attached to the level curve. Think about it being based. It's based. The gradient vector field is based. We should own that. Sorry if you're outside this political discussion, it's fine. But anyway, here's a sad picture of a random collection of 1, 2, 3, 4, 5, 6, 7, 8 sample vectors from the gradient vector field. And I don't know, maybe this is the, apparently this circle has, so there's different ways of drawing vector fields, all right? So some people draw vector fields so that the length of the vector actually indicates the magnitude. But many softwares don't do this. Like, they just pick a standard length, and then the density of the number arrows indicates the magnitude. So like more arrows of the given fixed length that it's using to plot indicates a larger magnitude. But if we do indicate the length of the vector field by its magnitude, it's like these vectors are actually representative directly of gradient of f, right? Then apparently this circle must have a radius smaller than I guess it depends on how, let's see here. To me it looks like the vectors I just drew are smaller than the radius of the circle, right? So is that even possible? Now, if I'm drawing this, this can't be right, right? How long should these vectors be? They're supposed to be twice as long as r. So let me draw one out here. So like r vector is this. To this point right here, that's the r vector, right? So 2r would be like this, but if I'm basing the vector field at the point in question, then this would be the gradient of f at this point P. So with that in mind, the gradient vector field, if I drew the vector field in terms of the length of the vectors approximately correctly, it would look something stupid like this, right? Which is why you don't typically see people drawing vector fields directly indicating the length of the vector field, because it just makes for really obnoxious pictures. So usually we don't insist on the length of the vector field, the length of the vectors of the vector field being illustrative of the magnitude. So anyway, these are these are issues you have to think about when you actually think about plotting a vector field. Right? Well, what is a vector field? A vector field is an assignment of vectors along each point in an object, right? So how many vectors is enough to illustrate the idea? So I think this picture is pretty cluttered at this point. Let me try to redo it over here. So let's suppose we're having, this is our level curve, and so usually I just do something like this, just to illustrate the direction. Again, would these be accurate to the? Well, here, let me fix it. Let me make my picture easier to graph. So, it's like example 2. What if I did something like f of x, y, excuse me, equals to 1/10 x squared plus y squared. See, then my gradient is what? It's like, 5x, 5y. Wait a minute, that made it worse. I can't do math. Is that right? Let's try that again. Make that a 20. There we go. That's what I want. So then I'm looking at x over 10, y over 10, right? So now my vectors are too long if I'm going to directly illustrate the vector field, right? Like if this, for example, was 10, this is 1/10, right? X, y, which would be 1/10 r in my current discussion here. So I should have these vectors to just be, 1/10 the length. All right. Sorry, this conversation is kind of boring, but it's a necessary one for us to have at some point. Because the question is, what do we mean by plotting a vector field? There's not universal agreement on this, like I said. Something like that, maybe. Now, why did I just draw that many? Really no reason, right? I could add that many vectors. It would still be a good picture of what's going on. Although I think to really put what's going on, I should maybe add, like another, maybe another circle in here. Let's say that one's what, radius 3 or something. I don't know, 2, whatever. And then, of course, I've got little bittier vectors in here because it's smaller and it's just, I don't know, I can't do it very well, but you get the idea. All right, so the larger point here is as we think about the gradient of f, what's it doing? If you had to describe the gradient of f, points where? In the direction in which f levels up. So the gradient vector is pointing in the direction in which you're finding larger level curves. Did you see that? It's pointing out where r squared is getting bigger and bigger and bigger. Okay? If example 3, we look at like f of xy equal to, I don't know, say y minus 1 over x, right? And if we look at that equals to a constant, what's the gradient here? Well, it looks like we got minus 1 over x squared, right? Except, do we have that? What's the derivative of minus 1 over x? Am I right?
1 over x squared.
1 over x. I got an extra sign in there, right? So, like that. Okay. What do these curves look like? Can you graph these? What are we looking at here? We're looking at y is equal to 1 over x plus a constant, right? So if I wanted to graph these, and we could, what are we up against here? We've got, well, c equals to 0. What's c equal to 0? It's this guy, right? Here's c equals to 0. That doesn't curve up at the end. That's just me. And then what happens when you do like c equals to 1? What do you do? Shift up 1, right? So it's something like this, right? How about c equals to, and this kind of just continues on, right? See, there's a whole family of these guys, like it just like this. And they all kind of get drawn in down in there, and these ones go like that. So there's just a whole family of stacked hyperbolas, right? There's one place where this family of level curves never gets to, which is what? 0, right? X equals to 0, not part of the story here. So the y-axis, something special happens on the y-axis, right? From this geometrically. Now, what does the gradient vector field look like here? So let me just kind of plot it. It's always going up 1 in the y, right? But what happens with x? So it's always going up 1 in the y. So if we could go really on far, let me just focus on this one blue curve here, and I'll draw the gradient vector field on that, sort of. Do my best. So if x is really big, the gradient vector field does what? It just points directly up. And essentially the x component 0, right? So it'd be like this here. Now, what would it look like as you get over here? It's always length 1 up, right? But it starts to point a little bit over, and a little bit more over, and a little bit more over, until finally it gets over here where it's doing something like that, right? But if we could plot it properly, the gradient vector field, what we'll be able to argue by calculus today, is that the gradient vector field has to be perpendicular to the level curves. That's what we're gonna see from the calculus. And you can start to see it in the examples if you just look, right? All right. Any questions? Does everybody feel like they have some concept of how you would plot a gradient vector field by hand if you had to? No? Well, I would recommend not doing this by hand, honestly. But the procedure is, first of all, understand what the curve looks like, and then just pick points along the curve. You pick a point, and then you just plug in the gradient vector. So for example, if I'm at the point on the red curve, let's say, right, this one, but I think I put c equals to 0 for the red one, right? So on the red curve, we've got y equals 1 over x is the curve. So if I look at the point, pick a point. For example, 1, 1 is a point on this curve, right? So see that? 1, 1 is a point on the curve, because 1 is equal to 1 over 1. So then I pick my point, 1, 1 is the point to consider. And then I take nabla f, and I plug in 1, 1. And what do I get? Well, 1, comma 1, actually. Because I plug in 1 over 1 squared, which is 1. And so there you go. That is the thought process to specifically calculate the gradient vector field at that one point. Now you just need to repeat that process about 50 times for a given family of curves to get like a full, reasonably halfway okay picture. And of course you want to space your points out, right? You want to pick, I would say as a general rule of thumb, if you're going to do it by hand, pick maybe 3 or 4 level curves that are representative of the graph you're trying to fill, and then pick at least 4 or 5 points on each one of the curves in order to add vectors to those. That would give you a pretty decent, hand-to-hand combat vector field. I've almost never tested on this because what did I just talk about? I talked about picking like 25 points, putting in 25 points to a vector formula and graphing 25 vectors. Like, is this a good question for any kind of time pressure test? No, obviously not. And in fact, the larger point here is we really should use a technology of some sort or another to graph these things. Actually, I'm much more interested that you understand conceptually what's going on than you'll be able to, like, graph these by hand. So let's get to it. Let me show you in the notes some examples of gradient vector fields so we can appreciate what's going on. Before I go on from these examples, though, just let me point out something. This center point is special. It's a critical point. When the gradient vector field is 0, that means something funny is going on, right? So the gradient vector field being 0 is the one place where this isn't a curve. That's not an accident, right? It's a point. And the same thing happened for this one. Example 2 is essentially the same example, right? The gradient vector field 0 at the origin. How about this one? Is the gradient vector field ever 0? In example 3, no, the gradient vector field's never 0. It's always got this 1 over here, right? Which speaks to the fact that there's not what's called a critical point for this one. You might say that the whole y-axis is a critical line, but actually, in fact, that would be true, because my definition here, do you guys remember the definition of critical point from Calc 1? What was our definition? Remember we talked about Fermat's theorem and all that stuff. If the derivative either doesn't exist or if it's 0, it's a critical point. And we learned that those are exactly the points where the function could have a max or a min, right? Doesn't have to, but it could. Same thing happens here. A critical point for a function of several variables is a point where that function either, it could have a maximum, it could have a minimum, it might be neither, right? Could be even a point of discontinuity, or a point outside of the domain, like this. Example 3, the whole y-axis is outside the domain of the curve, of any of the curves. So hopefully you guys are starting to feel more comfortable with how to calculate the gradient vector field, excuse me, the directional derivative at a point. So now we're talking more about assigning a gradient at each point and thinking about it as, we're now thinking about what happens as the point varies. And as we think about it as the point varies, that brings us to this concept of gradient vector field. So we use nabla f, again, the gradient vector field on U. And so the technical definition is just to each point P in U, we assign the vector field nabla f of P. This is what a vector field is. It's an assignment of a vector to each point along some object, all right? Think of it as gluing a vector. So it's kind of like a hair transplant. Got some guy with no hair, and then he goes to the doctor and they put a bunch of hairs on his head. That's like an assignment of a vector field to his head. Something like that, Here's one. This would cost you a lot of money. Well, not really. They assign like thousands of hairs. This should only cost like $20, Wouldn't look too good. I don't even see anybody getting green hair transplants either. And that would be an interesting tattoo, Okay, so here we're looking at the one I foolishly attempted to plot by hand. And this is it's indicating the magnitude of the vector field by the length, but I don't think it's dogmatically making the length of the vector actually descriptive of the magnitude of the gradient vector, because that kind of picture is just overwhelmingly technical. It's not a good picture. This gives you a sense of, okay, the gradient vector field's getting bigger as you go farther out, but also it's always pointing away from the origin, directly out from the origin. Now, this picture also has superposed on it, these are called contour plots. So a contour plot is a level curve. Well, a contour plot is when you plot more than one level curve at once. This is what a contour plot is. I've been making contour plots over in my examples 1 through 3. These are all contour plots. See, the contours are the different level curves, right? And that language goes back to like topographical maps, right? Where you have, if you ever guys have seen the topographical map, you like map altitude, you draw these little lines of constant altitude. That's a contour plot, all right? Let's see here, so here's another one. So here I'm looking at x squared minus y squared. The gradient vector field is 2x minus 2y. And so here's some plots. So if we set x squared minus y squared equal to a constant, you either get a hyperbola that opens sideways or opens vertically, right? And do you notice how the vector field works there? So my question to you guys is, as you look at the hyperbolas there, if I can zoom it in, I'll zoom it in a bit. Second here. In which direction are you going to higher level curves? You're like, well, that kind of depends on where you are, right? Let me zoom in a bit here so we can see it better.
Would just be away from the origin in the x direction, or on the x-axis?
Let's see here. Well, away from the origin on the x-axis, I think that, well, first of all, it's changing less at the origin, right? You see that the origin is a place where the gradient vector fields are all going to 0. The origin's a critical point. All right? Now, at this critical point, we have the gradient vector fields pointing up, right? So it's a higher level curve than these curves down here, right? But how about up there? The gradient vector field's pointing down. So the origin's a lower level curve than those up there, right? Apparently. And let's see, this way, you're leveling up if you go out this way. You're leveling up if you go out that way. So we have this interesting point in the origin where we're at a lower level than all these and all those, and we're at a higher level, going high, up, right? The gradient vector field. So this is a maximum if we look along the y-axis, but it's a minimum if we look along the x-axis. So this means this critical point would be what's called a saddle point. Because if you look at the surface, z equals f of xy, it would look like this one way, but it would look like that the other way, like a saddle does. Now, I think I have some pictures. I have some pictures which we'll get to here, but let me just continue with my examples for now. This is kind of a stupid example, but it's actually important. What's the gradient vector? If you just take the constant function f of xy equal to x, what's the gradient vector field? It is x hat. This is the x hat vector field. It's just the assignment of one unit, the horizontal vector, length 1 at every point. What does that vector field tell you? It tells you which direction x is increasing the fastest. That's its meaning. All right? That's its meaning. Now this is neat because, well then, come on. I said go. Let me go down. Ah, the double scroll has got me. Ah, the double scroll. Sorry, guys. Of course, if I have x hat, I can't help myself but to put the y hat example, right? Here's the y hat vector field. And I've even included these are level curves of y. Y equal to a constant. The way this color coding works is the blue are lower, the red are higher. So as you can see, you're going leveling up in y like that. Contours are simply horizontal lines in this case, right? Y equal to a constant. Now, the really cool thing about this is if you think about it, if we can define some other coordinate system in terms of level curves, right? Say f1 of xy equal to a constant, f2 of xy equal to a constant. If these define the level curves which coincide to another coordinate system, then if I calculate the gradient of those functions and normalize them, that will give me the unit vector in the direction of increasing y1 or increasing y2. Like, let's apply this idea to the polar coordinate system. So like the polar coordinate system, there are the radial direction r is equal to the square root of x squared plus y squared, right? And theta, inverse tangent of y over x. I'll just look at the right half plane for the sake of specificity. Calculate the gradient of r, what happens? We've got partial derivative of x squared plus y squared, partial derivative of that with respect to y. How do these derivatives go? Well, we get 1 over twice the square root times the chain rule, right? Times the derivative of the inside function. What happens there? Well, we get a 2x. That 2 divides the 2 from the partial differentiation of the square root. So we just get that. But what is that? Well, that's x over r. That's y over r. Do you guys remember polar coordinates? What is x over r and y over r in polar coordinates? Right. Remember, it's x equals to r cosine theta, y equals to r sine theta. So x over r is literally cosine theta, y over r is literally sine theta, and is this a unit vector? It is, right? Cosine comma sine is a unit vector, so it's already normalized, and that shows you that r hat is exactly cosine sine. Now you could argue this by geometry just the same, right? If you just draw a picture and think about the meaning of polar coordinates, then that is a vector which points out of the origin and has length 1 at a point in the plane. But I didn't use geometry. I used calculus to derive this just now. Similarly, the gradient of theta, well, these derivatives are a little bit more fussy, but inverse tangent 1 over 1 plus the thing squared, right? And then I have to multiply by the derivative of y over x, which is minus y over x squared. When you multiply that through, you get x squared plus y squared in the denominator, and you get a minus y upstairs. This one, on the other hand, when I take the partial derivative with respect to y, I still get a 1 over 1 plus x squared, 1 over 1 plus y over x quantity squared. And then I have to multiply by 1 over x. So I multiply the top and the bottom by x to clear out the denominator, and I get this as well. So listen, those aren't, these derivatives aren't directly obvious. Like, you should sit for a minute and work them out, okay? Anyway, the point is the gradient, this is the gradient vector field to the angle function, right? This points the direction of, well, this points in the direction of increasing theta. However, that's not a unit vector, because that's actually what? Well, that's 1 over r times minus sine theta cosine theta, right? So if I want a unit vector in the direction of increasing theta, then I have to renormalize. I have to divide by the length, and I just keep the minus sine theta cosine theta. That points in the direction of increasing theta. Okay, so this is a procedure we can use to calculate the unit vectors that point in the direction of a coordinate system that we're given. And here's what it looks like. Now, there's obviously some problems here. This one's simple enough to understand. This is the r hat vector field. It points directly outward. This is r hat. It points radially outward from the origin at each point. This one, you see what's going on here? What's the problem is that the software doesn't quite know what to do at the y-axis, right? The software isn't quite robust to understand how to deal with the standard angle at that point. All right. Now, I have dodged that issue in my written work by assuming that x is positive. If x is positive, we're over here where life is happy. But here, x equal to 0, so we need a different definition for angle there. You could define the angle like in the upper half plane or the lower half plane using like an inverse cotangent of x over y rather than y over x. So anyway. Yeah. You can move the discontinuity of the angle wherever you want. In fact, you don't need a discontinuity on the axis if you're willing to use a more subtly defined angle function. You can relegate the discontinuity to just one ray where the angle jumps by 2 pi. But this is the subject matter of complex analysis, so let's leave it for the moment. Although we could talk about it here, but it's kind of not super on target for today. Let me not do that. Excuse me. So I've been claiming the gradient vector field is perpendicular to the level curve f of xy. I'd like to prove that with calculus today. So let me finish my pictures. Here's an application. Excuse me. If v is the voltage function, then the gradient to the voltage function actually is so the way voltage works, and it's related to the electric field is equal to minus the gradient of the voltage. So the electric field actually points in the direction in which the voltage is decreasing. This corresponds to the fact that, like in electrostatics, the electric field pushes positive charges in the direction of lower voltage, right? Nature likes to make voltage decrease. That's the natural direction of things, which is why you have to put a minus in for the relation between the electric field and the voltage, like up there. So the application, and I know you guys haven't all had second semester physics, and that's cool, but this relation right up here, you see that is the relation between the electric field and the voltage function. Constant voltage curves are called equipotentials, equal voltage curves. Those are level curves for the voltage function. But notice the minus reverses the story that we tell in here, because that minus means that if you go in the direction of the electric field, you're going to lower voltage levels. So that's an application of what we're doing right now. That's pretty important to some of you. Let's see here. These are the pictures I want to show you guys. So right here, let me explain the meaning of this picture. So we're looking at, on the one side, we're looking at, there's actually a couple different things going on here. This one's a little bit complicated. Let me see. Rats. This one's complicated. Well, that one's okay. Yeah, let me look at these instead. I don't want to look at the other one because it's got two different surfaces plotted on it at once, which is like it's too busy. This is easier. So here, I have a function 2x plus 3y, right? And so if you look at z, if we look at z equals to 2x plus 3y, what is that? It is a plane, right? We know how to graph z equals 2x plus 3y. It's a plane. What are 2x plus 3y equal to a constant? Well, those are these lines in the xy plane, right? So these are contours. Those contours correspond to specific levels in the plane, and the color coding is consistent here. This is how the picture is made. These pictures are made with something called Maple, which sadly we do not have. But I'm sure you could do this in Mathematica if you had a lot of time. But anyway, so here, this is the x squared plus y squared graph again. These are the contours of x squared plus y squared, right? And looks to me like here, we're making blue the larger values and red the smaller values. We've done the opposite in other pictures, right? So you got to kind of watch the color coding. But you can see what's going on, right? As you get into the more blue parts, you're getting to the higher levels. And you can imagine, the way I think of it is the contour plot, you can think of those as just kind of like raising up off the xy plane to form the surface. You guys ever seen Stargate? Nobody's seen Stargate. So you know what I'm talking about. There's this thing where they've got these rings and they just kind of like whoop, 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 whoop. It's like that. Yeah. Well, at least, fine. There was one. It counts. Anyway, you don't need to see Stargate to understand level curves. It's true. Here is, it's kind of hard to see, but these is the x squared minus y squared contour plot. There's that saddle surface I was talking about in 3 dimensions. Let's see here. Here's a funnier one. This one, we're looking at the cosine x, f of xy equal to cosine x. So it's the same for all y, right? So that means whatever the surface, whatever the graph of this looks like, it's got this it's just repeated over and over and over again for every x. And so it looks something like this. So these are the level curves, and they just keep repeating as you go through like that. And so it's basically just the cosine graph, right? Just repeated over and over and over again at each x. Or maybe y, I forgot what I was. Well, this is y, that's x. I'm doing cosine x, so that means I'm repeating it at each y, I should say. I need to get my story straight here, guys. But anyway, let me stop this show and tell time, and let's talk about the calculus which proves what I'm saying, all right? Because that is really the next calculational the next big calculational if this thing will shut up and let me talk again here. So the next big calculational business for us is chain rules. Now we will not finish chain rules today, right? We will not. But I can share with you at least a couple of chain rules that are relevant to us. So here's one. If we have a function, all right, which is, let's say, from R2 to R, and a path, let's say gamma, let me use R, my bad, R, which is a mapping, let's say, from R to R2, all right? Then we can define a composite, right? F composed with R is a mapping from R to R again. And the definition of this is F composed with R of T is equal to F of R of T. This is the composition of maps. All right? So now this R, a lot of times we'll write R as like, you know, whoa. Point taken, I guess. I don't know. Maybe some guy was trying to see how high he could kick the wall or something, you know. Is there another classroom on the other side? This is the hallway, right? Probably just somebody practicing their jumping spin kick or something. People do that. Anyway, so the point here is that the derivative with respect to t of, and I'm going to write it in a slightly different notation here, f of x of t comma y of t, all right, is equal to, I'm going to write a few different notations for this, guys, but what it is it's partial f partial x at the point x of t, well man, this is going to be really obnoxious, you'll forgive me here, times dx dt plus partial f partial y of x of t y of t. Man, I hate to even write this. Dy dt. In a much more elegant notation, what this is the gradient of f evaluated at r of t dotted with dr dt. See here, dr dt is dx dt dy dt. I'm not going to prove this chain rule for you today, okay? I'm going to try to explain all chain rules at once in a future day, which is probably my greatest abuse in this whole course, because I will use some matrix stuff to do that. To understand the chain rule, we have to understand it from a matrix perspective. That is the truth. I can't paper over that. But you don't have to understand matrices to learn the chain rules in here by any means. There's like a natural pattern that they follow. So let me just write this. Let me write this in an uncluttered way, okay, guys? So what I'm saying here is that df and dt is actually equal to partial f partial x dx dt plus partial f partial y dy dt. That's all I'm saying here. All right? So let's do an example, yeah? So example 4, I guess. If I have f of x comma y equals to, oh, let's say x squared plus y squared. We like that one for today. All right. And I have r of t is equal to, oh, I don't know, e to the t cos t, t cubed. Right? And I want to calculate d dt of f of r of t. Then what I do is I calculate partial f, partial x times dx dt plus partial f, partial y times dy dt. Now what's that look like here? Well, that looks like partial f, partial x is 2x. Dx dt is what? Actually, let me put in some more details here just to make it uglier, because all of a sudden I'll be out of time here and then I'll be sad. So this is, again, this is what? This is 2x. This is 2y, right? So you notice that the full-throated chain rule says you have to evaluate the gradient at the point you're composing the function with. So I do 2x, which is what? 2 e to the t cosine t, and then I have to differentiate that, right? What's dx dt? Well, it's kind of ugly, but it's e to the t cos t, product rule, right? Minus e to the t sine t. All right? And then plus 2y. Well, what's my y? That's 2t cubed. And then times the derivative of dy dt is what? Well, y is equal to t cubed here, so 3t squared. And there you have it. That, my friends, is the chain rule for a function of two variables composed with a path. Now, does this particular path I made have anything to do with this function whatsoever? Not really, right? What happens if instead I look at the... first of all, any questions about this before I say more? Okay, yeah?
So what exactly does that derivative represent? Is that like the change the magnitude of f in respect to the
It is telling you the rate of change of f along the curve. So, which is somewhat complicated here. I mean, I can't even, so now that you've asked me that question, elaborating on that further is very difficult for me because I don't know how to graph this at all. But if you could graph this, right, which is some wacky curve in 2 dimensions, then along that curve, this is the rate of change of the x squared plus y squared function at time t. Check this out though. So definition. R from, let's say, R to R2 parameterizes f of x comma y equals to c if, and I really should, I'm being lazy here, guys. I really should say I, a subset, my bad, I a subset of R, because the domain doesn't have to be the whole reals, okay? Like the domain could be a subset of the reals. So if f of R of t is equal to a constant for all t in the domain of the parameterization. So what I'm saying here is a parameterization of a level curve is a path that when you plug it into the level curve, it solves the defining equation. So theorem, the gradient vector field is perpendicular to the path which parameterizes f of x comma y equals to a constant. Or maybe a better thing to say here would be that the change in the function along its parameterization is 0. These are two sides of the same statement. Here's the calculation. So we're given that f of r of t, right, is equal to a constant. This is what it means to parameterize the level curve. All right? Differentiate this equation, what happens? Well, now we know the chain rule, right? So if we differentiate this, what happens? Well, you see the right-hand side, side of this story we have known since calculus 1, right? The derivative of a constant is 0. But the left-hand side, the chain rule, says is the gradient of the function evaluated at the path, all right, dot product with dr dt. So what this is saying is, if I have some level curve, right? If this is my f of x comma y equals to a constant, right? And the parameterization, maybe the parameterization just covers this part right here, okay? Maybe this is like a typical r of t, all right? What this is saying is that the gradient vector field at that point has to look like this. Or what? I mean, it's perpendicular to the green line. What's the direction of the red line? It's perpendicular to the direction of the red line. What's the direction of a path? Remember, it is the tangent vector field, the velocity field, if you will, right? So, this is the, this right here, if this is the direction of it, right? There's your r prime, your dr dt, right? Those are perpendicular. What else is this saying? This is saying that the change of the function, right, df dt equals to 0 along a parameterization of f of x comma y equals to c. I mean, by golly, I would sure hope so, right? If it's a parameterization of the level curve, well, it better not change the level along the parameterization. It wouldn't be a very good parameterization of the level curve if it was changing, wouldn't it? But what this means is that the gradient vector field to the level curve must be perpendicular to the level curve itself. This is the bedrock on which we build many ideas in this course as it relates to level curves and soon level surfaces, because essentially the same calculation we'll go through in 3 dimensions. We'll talk about that like tomorrow probably, but any questions? So the reason that wasn't 0 is because that was not a parameterization of a circle. To, example 4, this one, right? If I instead have looked at what's the parameterization of this circle, how about this? Well, cos t, sine t, right? And so what's dr dt then? Minus sine t cos t, right? And what happens when you take the dot product of this with the gradient of f, which is what, 2x, 2y? See, if you take the dot product of this with that, once you evaluate it at cosine sine, you get 0, right? And is that surprising? What happens if we take f of cosine sine? What's that? Cosine squared, right? Sine squared. What's cosine squared plus sine squared? It's 1, right? So you can think about this theorem if you look at a parameterization of the circle and how it works out. Now, some of you at this point are going to be like, but I can just plug in sine squared, and I can plug in cosine and sine into this function, and I can just differentiate it as a function of time. I don't need the chain rule, right? That's true down here too. You could have just plugged in x equals to that, y equals to that in there and differentiated with respect to time. That is true. But it will not help you understand geometrically what's going on, which is something we need to do. Anyway, that's all for today. Thanks, guys.